This morning, we're going to talk about something that's at the heart of what many of you do within your organizations, which is building and operating ArcGIS systems, enterprise-class systems. The need for it is there because technology is evolving rapidly. There's no doubt about it. Building and deploying such systems, operating them, is a shared responsibility. It's a responsibility between us, Esri, who build the software, as well as you, playing the various roles that you play as developers, as system integrators, and more, IT administration included. Embracing more and more of these opinionated standard architecture patterns is also very fundamental and key. Following the best practices is very essential for your success. So let's start with what exactly is an enterprise GIS system made up of. It's, of course, mapping and analytics. That's the core of an enterprise GIS system. But it's built on an architecture that's also enterprise class, works with your enterprise data. And then, as much as it's made for various user personas who come into the system and use it in various ways, there's also automation that's built in. And it's designed to incorporate evolving technologies, AI included, and doing it all in an enterprise manner. And if you look at it from the lens of IT, as an IT platform, you can see that it's the full stack, right from infrastructure to data to services, apps and APIs, and workflows that it supports. And there are many implementation patterns and deployment patterns that suit you based on your conveniences and needs. You have Pro, and then you have Enterprise and Online. And of course, you can extend and experience that through web and mobile experiences and build upon this as a developer. And all of this is captured as a well-architected platform that supports your mission-critical systems and applications. But as you go through the anatomy of such a system, you see all of these good characteristics that are desired by IT. But most importantly, I want to focus that it's enabled by people and processes, whether it's the strategy or the governance, how you adopt it, and how you plan for capacity and so on. That's how a comprehensive system is built. The other aspect I want to point out is that you build systems, business systems, that meet the needs of your organization. You take enterprise IT into account, you build these business systems, and ArcGIS goes from being a platform to a system, like the ones that you see here on the right. Now let's look at a well-architected system. It comes with various patterns of implementation, like you see here. And then you take into account these IT pillars. These are the desired characteristics of any enterprise-class system. And then, as you fold these things together, you get best practices. And this best practice is what we call as a well-architected system. And if you look at the architecture of such a system, it's the full stack like you see here, starting from your data, your persistence of these data stores, and then translation into various information models, including the feeds that come in, and then being able to access them as data management services, mapping and visualization, analysis. And then the representation of you as a user within the portal, the sharing model, what access privileges that you have, what apps and APIs you have access to. What you'll see is that in all of these, the system pillars are taken into account as we build the system, and it's also ready for the future, where the future is now, we could say, bringing AI into the picture. It supports AI agents, AI models, and the ability to build agentic apps like we saw yesterday. Now, let's start with the first pillar, a pillar of integration. ArcGIS supports out-of-the-box many other systems, supporting system-to-system integration across the enterprise, like the ones that you see here. This is geo-enabling enterprise business workflows, and there's direct support from ArcGIS for many of these, like for asset management, AEC, and work management, and so on. But there is a need often that your domain or your organization has very customized and specialized needs that you want to be able to extend the IT system of ArcGIS. And there are three ways to do it. You can extend within it and then stretch out, And you might be able to do that by intercepting every call and response, or you integrate with other systems using APIs. And if you drill deeper, let's say for ArcGIS Enterprise, and take its components into account, the main components are portal and ArcGIS server. So how can you extend and integrate that can translate to things like webhooks, organization webhooks, and then being able to receive events from elsewhere into notebooks that you can execute for automation workflows. And then, of course, the same thing with server components like geoprocessing and feature services. Then there are extensions like server object extensions, custom GP tools that are exposed as services, as web tools, Geo AI models, being able to access your external data sets that we don't have direct support to through custom data feeds. And then being able to intercept every request and response, because there, none of the clients are aware of this backend technology, and they work out of the box without any changes. No, so let's start off with looking at business system integration, how you can take multiple enterprise systems and integrate and work with each other. For that, I'd like to introduce Pankaj to show us how it's done. Pankaj?
Thank you. For commercial property insurance company, maintaining a digital record of its assets in a system like ArcGIS is important. This application maps commercial properties with their policy status alongside layers like fire station, crime incidents, flood zones, demographics, all critical for risk assessment. Field inspectors and GIS analysts uses this application to evaluate the property and store inspection details in ArcGIS. Sales team manages customer account, location intelligence, and policy details in Salesforce. Expectation here is when a new property is inspected using this app, the Salesforce must be updated with the enriched location intelligence. And when policy details are finalized in Salesforce, map should reflect it right away. Let me show you how Service Interceptor makes this possible by running custom code inside an ArcGIS server service at request and response level. Here is the code. I built this project using ArcGIS Enterprise SDK with Java. This annotation binds the interceptor to a specific hosted feature service. Next, for each incoming request, it checks if it's an edit operation. Then, it validates the input and enriches the request payload with the location intelligence by querying available critical layers. It then sends the enriched data to Salesforce, keeping both the system in sync at the moment of edit. On the response side, when query comes in, it pulls latest policy details from the Salesforce and injects them into outgoing response. Finally, this project is packaged into a single interceptor file ready for the deployment. Now, as an ArcGIS server administrator, I am uploading the same interceptor and registering with it. Registration process is simple. At this point, interceptor is fully operational. No downtime, no service restart. Let's see it in action. Imagine that new insurance opportunity is available for this property. The sales team has created a new account with the address details only. The property inspection and location intelligence data is not yet available. Now switching the role to a field inspector. Field inspector is on site at the same property and updating the inspection details like roof condition is good, number of floors are 2, fire safety is good, this is a building age, and so on. Upon successful inspection, the policy status is changed to inspection completed, signaling that the interceptor has executed in the background. Let's check the impact of the interceptor in Salesforce. For same property, the inspection details are populated as is. But look, location intelligence details are also populated, even though I did not enter them in ArcGIS. Interceptor calculated them based on available critical layer and sent them to a Salesforce in real time. All of that happened during request interception. With this location intelligence and appropriate coverage detail, the policy is finalized in the Salesforce with the status is set to active. Back in the map, for the same property, policy status is now active, and upon querying, it's pulling the latest policy details live from the Salesforce through response interception. This is how the service interceptor keeps the two systems connected and up to date. In summary, the service interceptors are lightweight and powerful way to connect ArcGIS Enterprise with various business systems without changing the client applications or modifying the backend services. Thank you. Back to you, Jay.
Thank you. Thank you, Pankaj. What you saw there was extensibility and integration across enterprise systems, Salesforce in this case. So this is what it looks like architecturally. You have a request that gets intercepted, and you're also able to synchronize between Salesforce and ArcGIS. Next, we'll look at what is arguably the most important pillar, reliability, and oftentimes observability and scalability also are related to it. For that, I'd like to talk about ArcGIS Enterprise on Kubernetes. It was built cloud native from the ground up. It's fully automated system for distributed computing. You get capabilities as microservices delivered as containers. And because it follows standards of cloud computing, Kubernetes in this case, it's able to run natively across all of these cloud platforms. And it's DevOps ready and friendly. A key aspect that we worked on was the default availability of the system. As you can see, by default, the standard availability is already highly available, and it's ready for most production systems. Then, of course, you can elevate it to another level with multiple availability zones. A key thing I want to point out here is the aspect of recovery point objective, which is how much data loss you can afford. That happens before you lose something. And then the recovery time objective, which happens after, which is what is the time to recovery and how much time you can have as downtime. Restoring from backups, extremely important. It's very low cost. And I don't know how much to emphasize on it because many of you need to have that minimally. And then you have enhanced disaster recovery, which is multi-region and hot standby support that we added. Now, this is what it looks like. If you have a cluster across many availability zones, we make sure all the data, as well as the compute, the services, are also spread across all of these. And you have a global traffic controller that knows how to direct them. Now, if you have a multi-region disaster recovery system, this is what it might look like across the two clusters in different regions. If one goes down, automatically the global traffic controller will direct to the other one because it's on hot standby. With regard to performance and scalability, you can obviously scale the cluster. You can also scale each of the vertical pods in terms of their sizing, or the number of them in terms of horizontal pod or the scaling. The thing that I want to highlight for this year is cluster auto scaling. It's available through Carpenter and through our built-in systems, where you're able to scale the cluster automatically up and down. And instead of me reading and explaining what multiple replicas spread across AZs and isolated node pools with placement policy is, probably best experienced through a demo. So I'd like to introduce Andrew to show us how it's done. Andrew?
Thank you, Jay. I'm stepping into the role of an administrator of ArcGIS Enterprise on Kubernetes. My top priorities: making sure everything is running smoothly. System is highly available, scalable, and performant. Here's one of my solutions: fire warning applications. The challenge is the traffic can spike suddenly, even virally. And in those moments, system must respond quickly to maintain performance. We address those scalability challenges by rapidly adding two key components: pods and nodes. Pods are the smallest deployable unit. We start with 2 pods to provide standby capacity. Horizontal pod autoscaler, or HPA, will add more pods when average CPU reaches 50%. The maximum number of pod replicas is 100, each with minimum 1 CPU core as defined by CPU request. That is 100 cores, roughly 13 extra nodes. Therefore, timely node scaling is essential. In Kubernetes management tool like Lens, I can quickly see all my pods running and my nodes. For node scaling, I'm using Carpenter, the open source high-performance autoscaler. Carpenter also lets me define dedicated pools, such as here, for my viral services, so they don't spill over and potentially impact the rest of the cluster. With the node pools defined, we place our service onto it by providing the pool name right here. I use this observability dashboard to validate my design. It brings together ArcGIS-provided metrics such as errors, performance, and load, but also cluster utilization metrics. All this data is stored in Prometheus database and can be visualized in this Grafana dashboard. I started a load simulation a short while ago. As the load increases, more pods are added. And when those pods can no longer fit onto an existing node, the cluster scales out by adding more nodes into our dedicated pool. Next, we check for performance. Performance levels out and stays solid. Finally, check for errors, no errors. With that, we validated the system is both scalable and performant. That wraps up how we built a scalable system capable of supporting a service with viral load. But how about the hundreds or even thousands services with unknown load pattern? Manually sizing and resizing all of them might be a significant operational burden. That is why we're developing this new capability, Intelligent Sizing Advisor. Here's a quick preview. Advisor analyzes operational data, provides the actionable insights. Here we have a few severe cases. One is running out of memory, and the others experience CPU throttling. We also have a warning case, high wait time. That is essentially scale-up scenario. The remaining info cases are either unused replicas, scale-down scenarios, or deployments that require just minor resource adjustments. Users can apply those changes either manually or let the advisor apply them automatically. In conclusion, I hope this demo gives you confidence that you can effectively observe your system, that it will scale exactly when you need it to, but it's also that you can reduce your operational burden. Thank you. Back to you, Jay.
Thank you, Andrew. That was an example, better demo than spoken about, right? Next, we'll look at scalability. Feature services capability. Feature services are often used, and we've added a few new features in it. Last edit time, which improves your performance. Response caching, where you can cache the query responses and share it across multiple clients. And also CDNs, where for read-only kind of services, this is extremely important and necessary when it goes viral. You get a 14x improvement on that. Another example is Kubernetes being able to do massive batch processing and doing it at scale. Distributed raster analytics with raster functions and with GeoAI, where both CPUs and GPUs can scale massively. For that, I'd like to introduce Mubarakat to show us how it's done.
Thank you, Jay. Let's start with the result. This is a forest health snapshot for British Columbia, derived from thousands of harmonized Landsat and Sentinel-2 imagery. This layer highlights forest moisture conditions linked to risks like pine beetle activity and summarized to timber supply areas for strategic forest management. Lighter areas indicate lower moisture content compared to darker ones. And since British Columbia is more than twice the size of California, this solution is fundamentally a scalability and performance challenge, not just an analysis problem. So let's take a look at how this scale is enabled, starting with how the imagery is managed. We discovered the harmonized Landsat and Sentinel-2 imagery using the stack experience in ArcGIS Pro and manage them with a Mosaic dataset. This collection is then published as an image service, keeping the imagery both streamed and centralized, so the analysis takes place right next to where the data already resides. And that's what lets the analysis scale more cleanly. The analysis workflow is run in an ArcGIS notebook in ArcGIS Enterprise, with all processing executed by the raster analytics server. We begin by loading the imagery, boundaries, and other layers needed for the analysis. From here, the first major compute step is creating a consistent seasonal imagery. In this step, we create a summer composite using a raster function template. At a high level, we are combining thousands of temporal imagery to create a clean, cloud-free composite. This is CPU-intensive work over a province-wide extent, and ArcGIS Enterprise scales it across multiple CPU nodes, cutting processing time down significantly when scaling from 1 to 5 to 500 CPU pods. Now that we have our summer composite, we can move into AI-driven classification. Here, we generate a land cover map using a pre-trained model. The goal is to create a reliable forest mask so that all downstream forest health metrics are computed only on true forested regions. As raster analytics server compute scales up, time drops significantly, resulting in a 41-minute land cover map using 80 GPU pods. Now that we have our land cover map, the remaining steps are lighter but essential for turning analytics into decisions. Next, we compute forest moisture conditions using the normalized difference moisture index. And then we apply the forest mask so we can reduce noise coming from non-forested land cover areas. Finally, we aggregate the results to timber supply areas, turning pixel-level analytics into management-ready summaries. Now, the final question is, how does all of this behave under real load? Before I came on stage, I kicked off the workflow. What you're seeing here is the system actively scaling out in real time, spreading CPU compute across multiple distributed nodes so that large workflows can finish in hours instead of days. ArcGIS Enterprise combines centralized imagery, distributed CPU and GPU processing, and scalable analytics to turn massive data into quick, actionable intelligence. Thank you. Back to you, Jay.
Thank you, Mubarakat. So to summarize, these are some of the numbers you see in distributed raster analytics at scale, whether it's trillions or billions of pixels. You can see that even for a smaller number of GPUs, like you see here, you can still scale. And if time to answer is really important, that's possible too. Next, let's look at automation. And automation comes in various forms. There's infrastructure automation, there's DevOps automation, workflow automation, and then there's trigger-based as well as scheduled automation. And for that, we have various APIs that can make it possible. Probably best seen in a demo for automation and governance of your organization. I'd like to introduce Bill.
Thank you, Jay. Appreciate it. All of you deeply care about protecting data integrity, managing change, and auditing interactions. Today, I'm going to present 3 governance strategies of how automation in ArcGIS Enterprise can help you meet those needs. Strategy 1, conformance. This organization enforces standards for items that are shared publicly, including authoritative status, item completeness, and proper item classification. But how can we enforce these standards when a user attempts to share an item publicly? As in this rather poor web map example. To enforce this conformance, I've configured a notebook to run via organization webhooks anytime items are shared or updated. The notebook itself will determine if an item is being shared and with the correct groups, its item completeness and authoritative status, and also has it been marked with a proper public item classification, including any of its related dependent items. If any of these criteria are not met, the user will be notified to take corrective action. In my case, when my poor web map item failed to meet the standards, our automation kicked in, unshared the item, and sent the user an email with a list of violations and how to resolve each of them. Strategy 2, change management. This organization manages content and configuration changes through CI/CD pipelines. As an IT administrator, I'm going to use GitOps with GitHub Actions to handle my scheduled maintenance and content updates this Friday evening. Let's fast forward to our maintenance window. I have a pull request of changes that I'm going to go ahead and merge to kick off our automation. But let's review what these changes are. We're going to disable anonymous access to our enterprise. We're going to create a new group and assign some users to that group. We're going to update the information banner to show that the site is under maintenance. And we're going to publish curated content that is being promoted or migrated from staging to production through a group export package file. We have a number of GitHub actions running ArcGIS API for Python scripts that are automating our pull request changes. To check on the progress of these changes, let's refresh this page. And we can see that our information banner has been updated. Anonymous access has now been disabled. A new group has been created and users have been added. And our migrated content is being published and imported into a new group. CI/CD workflows, especially for curated content, promote disciplined change management and help us minimize those manual errors. Strategy 3, compliance. ArcGIS Enterprise audit logs provides the organizations insights into exactly how users are interacting with the system. In a security information and event management system, or a SIEM, you can query audit logs to find events such as items being unshared due to conformance issues, who performed that action, and organization setting updates due to our GitOps workflow. Now, as a security engineer, I'm interested in using audit logs to find indicators of a potential insider threat. With a notebook, I'm going to use notebook secrets to connect to my SIEM. I'm going to query for update item events. And I'm going to retrieve additional information from ArcGIS Enterprise for each of those events. I'm then going to compare the event actor to the item owner, and we are finding situations where users are editing another user's content, including changing another user's item's classification. This could be accidental, an approved workflow, or it could be that indicator that warrants further investigation. This notebook could then be automated via scheduled tasks to generate reports, or it could drive ArcGIS dashboards for near real-time status reporting. 3 strategies of automation in ArcGIS Enterprise: conformance to standards, change management of configurations, and compliance via auditing. a continuous loop of governance that gives us confidence that every change strengthens our system. Thank you, and Jay, back to you.
Thank you, Bill. Let's take a look at what Bill showed. It was conformance using notebooks, webhooks. It was change management with GitHub Actions, and then also having security information and event management through CloudWatch in this scenario, along with audit logs and displays in a dashboard. All of this part of automating your governance. Next, we're going to look at something very recent, the emergence of Agentic AI and how ArcGIS as an enterprise system is incorporating this into a massive workflow. This is really about taking your GIS to the next level, data, information, and knowledge in the world of Agentic AI. And for that, I'd like to introduce Shreyas to show us how it's done. Shreyas?
Thank you, Jay. For a local government, such as a county, managing parcel data, zoning, and taxation are important business workflows. But the data required for these workflows is very rarely available in a single system. Today, I'm going to show you 3 strategies that allows you to integrate your data with ArcGIS and prepare it for analysis. So let's begin. Here, I have parcel and easement data that is stored in a parcel fabric data model within an enterprise geodatabase. So our first strategy is to register this enterprise geodatabase with ArcGIS Server, allowing us to build these as maps and feature services, bringing it into our data model, and working with the data model, preparing it for analysis. So the first thing that we need to do is just simply publish the data as maps and features, and our analysis is ready to go. On the other hand, data associated with taxation is usually stored in the office of the county treasurer, oftentimes in their own databases. I'm simulating it using a MongoDB database instance, and you can see the tabular information that holds tax payments associated with our parcels. We want ArcGIS to have access to this information, but not necessarily own or maintain this data. This is where our second strategy, which is to use custom data plugins, comes into play. Custom data plugins are an extensibility pattern in ArcGIS that allow us to extend ArcGIS and create feature services for data sets like spatial and tabular data not natively stored in ArcGIS. So to implement custom data plugins, we have to write some Node.js code. So in this custom data plugin project, in my VS Code IDE, I have some Node.js code that's connecting to my MongoDB database instance. It's querying the data within it, given input query parameters, and finally converting that dataset records as GeoJSON format before returning it to the client. This project is converted into a zip file with a .cdpk extension and registered with ArcGIS Server. I've gone ahead and done that using Server Manager. So in custom data feeds, you can see that the MongoDB provider is registered and ready to go. One step that I need to finish is to create feature services that reference the tables that we saw earlier in Mongo. And our data is ready to use. Our third strategy is to use ArcGIS data pipelines. Pipelines are a visual tool to build your ETL workflows. In my pipeline, I'm copying the flood zone data, which is a data set shared by the county in their download store, such as Azure Storage here, all the way into ArcGIS Server as a hosted feature service, filtering it and projecting it along the way. I can run this pipeline right here in this application or schedule it to occur at a cadence. And the pipeline takes usually a few moments to finish. And it's done that. So with the 3 patterns, we've registered all of our data with ArcGIS. So let's go back to our parcel map and activate these layers. So the flood zone layer that was recently copied is available for us, as well as the tables that were using custom data plugins. They're all queryable and ready to go. So we can begin our mapping and analysis right here in Map Viewer. But to analyze parcel data, we would have to create multiple joins on our feature and tabular information. While this is easy to do, a more expressive format is to use graphs within ArcGIS knowledge. So first, we have to transform our feature and tabular data into a knowledge graph. And to do that, I've authored a Python notebook that uses ArcGIS API for Python that converts our feature and tabular information into entities and relationships. Goes ahead and creates those entity definitions and loads the entity data, and likewise with the relationship definitions and loads the relationship data as well. So let's go ahead and run these cells. The first one creates a knowledge service, an empty knowledge service, and the second one will start loading our data, and you can see that the data is being processed. Now, this takes a few moments to finish. So let's change gears now and look at this from an analyst's perspective. I am now logged in as a knowledge analyst with whom all of these layers were shared using organizational groups. I'm opening the knowledge graph that we just created in Knowledge Studio, a visual tool to work with knowledge graphs. And I can use it to introspect the data model or to query the data using Cypher queries. And Knowledge Studio is a powerful tool to work with our graphs. But I would like my organizational staff to have access to all of this information merely using natural language. And to do that, I've authored a Python agent in my Python notebook using an agentic framework called LangGraph. To this agent, I have defined a few tools, one to generate the Cypher query, and the other to run the query against our graph service and produce result. I've given it a connection to a language model along with a prompt that it's a helpful assistant that needs to solve this problem. The agent is then compiled and ready to go. So let's go ahead and test this agent. So the first query that I want to ask is find me all the parcels that have an easement and that have a lien against them. And as you can see, the agent has picked up this query, and it's using the natural language model to understand the query, using the tools to produce a query against our graph service, and finally run the query and produce result. So we have results from our graph service only by using natural language. So let's challenge it some more. See here, I want to know all the commercial parcels that are in flood zones. Now, this is challenging because we haven't defined an explicit relationship between parcels and flood zones. And the agent, along with our data model and tools, is going to understand that, and it's going to take advantage of an implicit spatial relationship. So when the natural language model picks up the queries, you can see that it's picked up an intersect spatial operator between the parcel polygons and the flood zone polygons and produced 883 commercial parcels that meet our expectations. Now, as you can imagine, this is incredibly powerful, and I'm driving it simply using natural language. I can map this data very easily. And convert this notebook as an interactive web tool to drive workflows in my organization. But I would like to push the envelope here a little bit more. I want this notebook to run autonomously when changes happen to the underlying data. So to simulate that, I've defined a query here that says, if a particular parcel were to change ownership, identify all the entities and relationships that will be impacted, and to generate all the downstream impact, maybe even departments that need to be notified. So the agent has picked up that query, and it's going to run through its set of tools to produce all the impacted entities and relationships for me to notify. And we are in solid territory with this notebook driving autonomously. So today we saw 3 different strategies to use Parcel Fabric, custom data plugins, and ArcGIS data pipelines to bring all of your data as powerful layers in your WebGIS. And now, with graphs and agentic AI, you can transform your data into knowledge, driving intelligent decision-making in your organization. Thank you. Back to you, Jay.
Thank you, Shreyas. That was pretty amazing. That's really the future of enterprise GIS, bringing business workflows in an agentic manner, giving rise to agentic GIS. So as you can see, Shreyas had notebooks, data pipelines, custom data plugins, all of these points of integration, but really at the end of it, it was all about agentic GIS for your business workflows. So to summarize, I would say in this journey of bringing a foundational geospatial and AI platform, we are in it together. We are here to help you build a well-architected system, an enterprise system that's also an IT system for many of you, a business system that solves real needs. And together, these are not just building systems. It's about architecting the future of intelligent, resilient, and integrated geospatial enterprises. And I hope this week we'll have the opportunity to interact and talk about it more.